Hi everyone, today we're going to do some mechanics and we're going to look at the following scenario. So we have a bowl, okay, and the bowl is basically just a hemispherical shell and the radius of that hemisphere is capital R. As you can see, I've marked that on the diagram here. So what we're going to do is inside that bowl we're going to place a plank, okay, so that's this slightly thicker straight line here, that's a plank, and it has a mass of capital M, and its length is going to be parameterized as some number alpha times the radius of the bowl itself, right? So the plank's length is alpha r. And finally, at one end of the plank, we are going to place a massive particle, and the mass of that particle is going to be small m. Okay, so we're kind of weighing it down on one side. And then the question we would like to answer is, when this system is in equilibrium, what is this angle theta? So I've defined this angle theta. So what angle does the plank make with the horizontal in equilibrium? Okay, so the first thing I'd like to do towards analyzing this situation is just think about all of the forces that are acting on this plank, right? Because in equilibrium, the net force is going to be zero, and also the moments and the clockwise and anti-clockwise moments or torques are going to cancel out, right? So the first thing to do is consider the forces, and so at the 2 points where the plank comes into contact with the bowl, there's going to be a normal reaction force, right, stopping the plank from falling through the bowl, and that's going to, assuming there's no friction, right, that's another thing we're going to assume there's no friction, it's a smooth bowl, right, if there's no friction, then the force between the bowl and the plank has to be perpendicular to the surface of the bowl at that particular place. Okay, so what I'm going to do is draw an arrow at this point of contact, and it is going towards the center of the hemisphere, right? Okay, so the reason for that is, I just said, right, it's a normal reaction force. Okay, so this force has to act normally to the surface of the bowl, but the angle between a tangent and a radius of a circle is always 90 degrees, right? So if this arrow has to point normally to the surface of the hemisphere, that means it's normal to the tangent of the hemisphere at that point, and therefore it must be a radius because the angle between a tangent and a radius is 90 degrees. Okay, so here we go. That's why this arrow points exactly along this radius. I'm going to call that force N1. Okay, so that's a normal reaction force N1. And then at the other point of contact over here, we're going to have another force. This is also going to act along the radial line, right, because it's normal to the surface of the hemisphere at that point, and let's call that N2. So that's these N1 and N2 forces. Those are the two normal reactions at either end. Okay, and the only other forces that we're going to have are two weight forces, right? So if we assume the rod is uniform, then its weight can be thought to act through the exact center of the plank, right? So exactly in the middle. If it's uniform, the center of mass is going to be in the middle, right? So I'm going to draw on this force capital Mg acting at the midpoint of the plank, and also this particle at the other end, right, is also going to have its own weight acting directly downwards. That's just going to be small m times g. Right, so those are all of the forces, and I'm just going to think for a moment about the angles that these forces are acting at. Okay, so I'm just going to mark on a line here perpendicular to the plank, and a similar one for this other weight here. Okay, and this angle here, right, this angle here has to be theta, right? So I think the quickest way to see that is, okay, so theta is the angle that the plank makes with the horizontal, but then this angle that we're looking at here, right, that's the angle between the vertical which is the direction that the weight acts in, the angle between the vertical and also this dashed line, which is 90 degrees, makes a 90-degree angle with the plank itself. So basically what we've done is taken this angle theta and kind of rotated this by 90 degrees, but we haven't, we've rotated the horizontal by 90 degrees, and we've rotated the plank itself that direction by 90 degrees to get to this, but we haven't actually changed the angular separation between those two lines. So that's still theta, right? And so this angle here, down here, is also going to be theta. Okay. I think we should define one more angle, which is this one here. Okay. So this angle here between the plank and this normal reaction, I'm going to call that beta, okay? And similarly, we're going to have this angle up here. That is also going to be beta, right? And the reason for that is because the two normal reactions are acting along a radius. Okay, so I'm going to draw a little diagram below. So this diagram kind of helps us consider the forces, but I'm going to draw another diagram below where I just consider the geometry. All right, so let's look at a circle, and we can draw on the plank as it's just a chord, right? It joins 2 points on the surface. Okay, and let's draw on 2 radii. So something like this and like that. Okay. So what do we know about this? Well, the length of the plank is alpha r, but these two, right, that side and that side, they both have length r because they're just radii. Okay, so that's why these two angles here, these things that I've marked as beta, that's why they have to be the same, right? Because this is an isosceles triangle with 2 sides which are both equal to r. Okay, so let's figure out an expression for what this beta actually is. Okay, so to do that, we know all of the sides, and we're trying to find one of the angles in the triangle. So I think a sensible thing to do would be to use the cosine rule. Okay, so if we use the cosine rule, we can say r squared, okay, is, the other side squared plus the other side squared, right? So r squared is r squared plus alpha squared r squared, and then minus twice the product of those two sides, so minus 2r times alpha r times the cosine of the angle between those other two sides, which is beta, right? So now we have an equation which involves beta, okay? And the r squareds cancel from both sides, and what are we left with? We get 2 r squared alpha cos beta is equal to alpha squared r squared, okay? And then we can divide by alpha r squared on both sides and end up with the following. Cos beta is alpha divided by 2. Okay, so now we know what this beta is in terms of the length of the rod, because remember that was given by alpha times the radius r. Okay, so now we've done some geometry. Let's do some actual physics involving these forces. So the first thing I'd like to do is take moments. Okay, so if I kind of label a few points, let's say that point at the top left is point 1, and this point, so these 2 points of contact are point 1 and point 2, right? If we take moments around, or moments about point 1, what are we going to get? Well, we don't have to consider n1, the force n1, because that acts through point 1. Okay, so we have to consider the weight of the plank, right, capital Mg. So that weight of the plank force is acting at a distance of alpha r over 2 from point 1 because it's at the midpoint of the plank, right? So that's the distance, and we want, because we're taking moments, we want the component which is perpendicular to the plank itself, right? So we're going to get alpha r over 2 times mg cos theta. So that's the moment of this capital Mg force about 0.1. And in that same clockwise direction, we also have this small mg force, right? But that's acting in a distance of alpha r rather than alpha r over 2. So we can add on alpha r times small mg and also times cos theta because we want the perpendicular component. And that has to balance this n2 force is providing an anti-clockwise moment about 0.1 as well, right? So that kind of, the moment of the n2 force is in the opposite sense of the moments of the two weights, right? So if we sum up these two moments of the weights, they have to equal the moment of the force n2, and that is going to be what is acting at a distance of alpha r, and to get the perpendicular component of that, we have to multiply our n2 by sine of beta. Okay, so there you go. That's the balance of moments around 0.1. We're going to need some more equations, right? Because what we're trying to ultimately solve for is beta, but we've got three unknowns. We've got what we're trying to solve for is theta. We've got three unknowns, which are theta, n1, and n2, right? So we're going to need three equations. I think a kind of logical next place to get another equation from would be to take moments about 0.2, right? Because then we can get an equation that doesn't involve n2, right? So if we look from the point of view of 0.2, there is a clockwise moment provided by force n1, right? So the force n1 is acting at a distance of alpha r away from 0.2, and its perpendicular component is going to be found by multiplying by sine beta. Okay, so we get alpha r times n1 sine beta, okay? And then there's an anti-clockwise moment provided by this capital M G force. That one is acting at a distance of alpha r over 2, and it has a perpendicular component of capital Mg times cos theta. Okay, so there we go. Only two terms in this equation because we could ignore both n2 and small mg because they act through 0.2. Right, so we need one more equation because there are three unknowns. I'm just going to label these equations as well, equation 1 and 2. And what I'm going to use to get a third equation is to just resolve the forces. And of course we have to choose a direction to resolve the forces in. I'm going to resolve along the direction of the plank itself. Okay, so if we resolve along the plank, what are we going to get? So the component of n1 along the plank is n1 cos of beta, right? And you can see that the components of the two weight forces along the plank are also acting kind of down and to the right. Okay, so they're acting in the same direction as the component of n1 along the plank. So we can add on big M plus small m times g, and to get the component of those weights along the direction of the plank, we need to multiply by sine of theta. Okay, and all of those components have to be cancelled out by the component of n2 along the plank, right? Because that's acting kind of up and to the left rather than down and to the right. So that has to be equal to n2 times cos of beta. Okay, so there we go. We've got three equations. Now we've done the physics. It's just a matter of solving these to find out what theta actually is. So the way I'm going to do that is, notice that equation 1 only involves n2, right? It doesn't involve n1. Similarly, equation 2 doesn't involve n2. It only involves n1, right? So we've got equations 1 and 2 that only involve one of the normal reactions each, and then equation 3 that involves both of them. So what we could do is take equations 1 and 2 and use those to substitute for the two normal reactions in equation 3. Okay, so let's actually do that, and it should become a bit clearer what I'm talking about. So we are going to substitute equations 1 and 2 into equation 3. Okay, so take equations 1 and 2, substitute them into 3, and what's going to happen is the following, right? So let's look at this n1 cos beta term. What we can do is, just from equation 2, we can say that n1, what is n1 equal to? Well, we can cancel these alpha r's on both sides. So n1 is just going to be big mg cos theta over 2 divided by sine of beta. Okay, so where I see this n1 here, I can instead write that as mg cos theta over 2 sine beta, right? And that whole thing gets multiplied by cos of beta. Okay, so I've just substituted for n1 in this equation 3. Then we can't really do anything for now with this next term, m plus mg sine theta. Okay, then we're going to do a similar thing for this n2, but we're going to use equation 1 to substitute for that, right? So again, we can cancel these alpha r's from all of these terms, and we are going to find that n2 is, well, there is a common factor of g cos theta, right? And so we can write n2 as big M over 2, right, because there's a divided by 2 in this first term, big M over 2 plus small m times g cos theta, okay, and then we have to divide by this sine beta, right, and then we also have to multiply by this cos beta, okay, so basically what we get is, after that we get a cos beta and divided by sine beta. Okay, so fair amount of algebra going on there, but we've done our substitution, and now it's just a matter of simplifying this equation to give us theta in terms of beta, right, because we've eliminated the two normal reaction forces. Okay, so very conveniently we have on the left big mg cos theta cos beta over 2 sine beta. We have exactly the same thing as this first bracketed term on the right hand side, right? So we can cross that off, and we can also cross this off. Okay, so we've just got rid of some of our terms, and what are we going to be left with? We're going to get big M plus small m times g sine theta is mg cos theta times cos beta over sine beta. Okay, and then of course we can cancel the g's, and if we put all our thetas on the same side, if we divide everything, we can do that by dividing everything by cos theta, right? So we got on the left hand side we get sine theta over cos theta, which is tan of theta. Okay, so tan theta has to be, well, we then also divide everything by m plus m. We get small m over big M plus small m. Okay, and that is multiplied by cos beta over sine beta, which we can write more concisely as the cotangent or cot of beta. Okay, so there we go. That's theta in terms of beta, and our final step is going to be to use this result up here to actually write cot beta in terms of alpha, because alpha was the parameter that the question is kind of working in terms of, right? So how can we do that? Cotangent of beta is cos beta over sine beta, right? So cos beta we know already is just alpha over 2, right? And sine beta, we know sine beta actually because sine squared plus cos squared is 1, okay? So sine beta is the square root of 1 minus cos squared beta, or in other words, just the square root of 1 minus alpha squared over 4. Okay, so we can also take this factor of 2 from the top and put it on the denominator to make this look slightly nicer. That comes out to be alpha over the square root of 4 minus alpha squared, okay? And finally, we are done because now we know that tan of theta is small m over big M plus small m times cot beta, which is just alpha divided by the square root of 4 minus alpha squared. So there you go. Given any combination of masses, right, the mass of the Planck, big M, the mass of the particle, small m, given any two masses and any parameter alpha that tells us how long the Planck is, we can say exactly what the angle that the Planck makes with the horizontal is going to be. So just as a way of checking our result and understanding what it means a bit more, we can consider a couple of limiting cases and see what happens to theta. So for example, if small m is much smaller than big M, right, or if small m, goes towards 0, basically, then because small m just appears on its own on this numerator, tan theta itself is going to go towards 0, and tan of 0 is 0, and therefore if small m is really small, then theta is close to 0, which is basically saying that when you don't have, when your particle has almost no mass, then the Planck is just going to settle in a horizontal configuration, right, because theta is almost 0. Which is exactly what you would expect, right? Because if there's no particle, then there's no reason for the Planck to choose some particular angle theta. You would expect it just to be horizontal. Okay, so that's in line with our physical expectations. There's another interesting limit we can take, which is when small m is really big compared with big M, right? So if small m is much bigger than big M, what's going to happen is that tan theta, well, what we're going to get is basically m over m as our fraction, the first fraction, right? Because we can just ignore big M if it's really small, and that just cancels and gives us 1. And we'd just be left with this alpha over root 4 minus alpha squared. But remember, that was just cot of beta, right? So if small m is much bigger than big M, then we get tan theta is, or I should put a roughly equal sign here, is roughly equal to cot of beta. Now, what does that actually mean? Well, what's going on here is that if small m is really big, what's going to happen is that the particle is just going to go straight to the bottom of the bowl, right? That's what you'd expect to happen physically. So if we were to draw out, another copy of this diagram, but when small m is really big, the particle would have just gone all the way to the bottom, and so we can draw a vertical line like that as one of our radii, and then there's going to be another line going up to wherever the other end of the Planck is, right? So our triangle is going to look like this, just so that one of the sides is vertical, right? Again, these are equal. And what's going on is that, remember, theta is the angle that the Planck makes with the horizontal, which is basically this angle here, right? That one there. And our beta is still this angle down here. Okay, so actually this relation, tan theta is roughly cot beta. If you think about it, because thinking back to basic trigonometry, tan theta is the opposite side over the adjacent side, and cotangent is 1 over that. So cotangent is the adjacent side over the opposite side. This relation is exactly what you would expect for two different angles in a right-angled triangle, and that's exactly what we have here. We have a right-angled triangle. Okay, so this limit is also in accordance with what we expect physically, so we can have some confidence that this general solution is probably correct. Okay, so there you go. Not an easy problem, but it is quite interesting, and it's always fun to consider these limiting cases at the end. So hope you've enjoyed this, and see you again soon.